frameworks to perform proprioceptive state estimation on a Lego robot. Here you can see an example of we're showing an Atlas robot with proprioceptive state estimation overlap with the ground truth. So you can see it's actually doing a pretty good job of doing the proper state estimates. And state estimation is actually a very important problem because, as you've all seen, lots of cool work happening in locomotion, but in order to account for slip, in order to account for various terrain mappings and different kind of unknown problems that you might have with locomotion, having robust and accurate and efficient state estimates is a very, very important prerequisite. We also just, so the main thing is that we choose to do proprioceptive state estimation is because it also helps free up computational resources for other things such as planning or mapping. We saw this amazing talk right before about using an offline planner, and so because offline planner be online, you now have more compute. There already exists a lot of great work in Lego robot state estimation, and so I just want to position where our work stands with respect to this. So the top row represents all filtering-based approaches, whereas the bottom row represents factor smoothing-based approaches. So the original work that used proprioceptive state estimation was the work by Michael Bush in 2013 that used the IMU as well as Kinematic legs. That was followed up by work by Nicholas Tella on that's applied to a humanoid with a factor constraint, or point foot constraint. And more recently, Zuyang Lin at the University of Michigan has done some state estimation using learned contacts by a neural network contact estimator. On the bottom row, we have VLENS as well as contact integration. So both of these are actually hybrid. What they do is they also use exteroceptive measurements. VLENS, the V and the L stands for visual and LiDAR. And contact integration also uses the camera information to do state estimation. But the important insight that we have from all this work is that all of these state estimators basically follow this one particular factor graph formulation. So all the x's represent the base states, and then you have the legs, and the subscripts are the time indices. And I'm using plate notation over here to represent multiple legs. So we're not just two legs, but also 4, 6, 8, you name it. And then at each plate, and the C1 over there represents the contact point. So it's basically saying L0, L1, L2 are all connected to the same contact point. So that's basically stand states. That insight is actually what we leverage in developing our proprietary state estimator, because now we can just use the factor graph and its very useful properties in developing our framework. So proprietary state estimation is preferred, but of course it is more challenging because normally you get cues from the environment using camera or LiDAR or GPS and a barometer. You get all this very useful information, but it's very slow, it's very computationally expensive, especially cameras these days. And those are sensitive to the environment, like differences in lighting, differences in pressure, differences in like the minor things in proprietary state estimator. However, proprietary state estimation doesn't suffer from those problems. Unfortunately, it is very noisy. IMUs, especially the ones on cheaper quadrupeds and cheaper humanoids, can be terribly noisy. They have very strong biases that need to be accounted for. And but the good news is they're insanely fast. They can go up to 400 hertz, and the Atlas robot, for example, has an IMU that runs at 1,000 hertz. So if you get 1,000 hertz state estimation, that's pretty awesome. And so we want to take that approach and basically model this entire problem as a contact slam problem. So your contacts are your landmarks, and your camera is your base of the robot. So basically, we're putting a blindfold on Atlas, as you can see. The cool thing about our framework is that it works on all Lego robots. We only use the IMU measurements, the joint angles, and contact measurements. Our framework allows for asynchronous measurements, so all the measurements do not have to come at time synchronized steps. They can come asynchronously, and we can still perform estimation accordingly. And it's much more robust compared to filtering because it's using the entire history of the trajectory rather than just the last step. As I already mentioned, we are robot model agnostic, and I will show results on the Unity A1, and Robotics Animal C, and the Boston Dynamics Atlas. And we show results both in simulation and on hardware. So the key difference for our work is that we model each link as in the kinematic chain. So the kinematic chain basically involves everything from the hip going down to the foot, and you have multiple links accordingly. So instead of having one forward kinematics constraint or one forward kinematics factor, we instead add this joint measurement factor for each particular joint. So as you can see on the right-hand side, we have the thigh link, the upper link, and the upper leg link and the lower leg link. And each of them has a factor that constrains between the two individual links. The nice thing about this approach is that each noise model between the links allows for non-trivial interactions, and also can model deflections based on the URDF. So for example, if the weight of the robot is very heavy and there's some deflections that you see based on the difference in the URDF that you got from the factory or from the manufacturer, our system can account for that deflection error. And yeah, and that's basically it. And to get to work on different robots, all you have to do is just give us a URDF and it just works. We construct a factor graph for you and we optimize. So the way we optimize is that, so a factor graph is just a graphical language for probabilistic modeling, where we have some unknown states connected by some nonlinear constraints. So the boxes represent nonlinear constraints, and the circles represent the unknown variables that we're trying to optimize for. And so we can convert this probability maximization problem into a variational optimization minimization problem. And so equivalently for this factor graph, on the right side, we have the optimization problem stated. Enough of the math, let's talk about some results. Just to position ourselves, if you only use the IMU and didn't have anything, just to give you an idea of how noisy IMUs can be, you can perform dead reckoning and try to get results. And as you can see, the IMU decides to fly up on the animal robot, and it doesn't even reach the end in simulation. And simulation, it was relatively noiseless. So, first, let me run through some results in simulation. It's very important to run in simulation because, if it doesn't work in simulation, it's not going to work on hardware. So this is sort of like a litmus test, like, hey, okay, it works well, then you can maybe deploy it on a robot and actually spend that hour and time and money potentially dealing with all the inconsistencies that come with work on hardware. The cool thing is, our estimator just works on hardware. Like minimal change, all you have to do is change some noise models, some parameter tuning, and just change the URDF. It's not a big difference, and as you can see, I'm showing results where we have three trajectories: the ground truth trajectory collected by a Vicon motion capture system, then and that's in green. And then we have the antibodies built-in state estimator, which is rendered in blue, and then we have our state estimator rendered in red. And as you can see, this is kind of like a Mario Kart ghost racer kind of deal going on. As you can see, it's overlapping really well, it's running really well. And we definitely have much more improved results where the absolute position error, or the absolute pose error, APE, is 74.52 for our state estimator versus 440.34 for the antibodies estimator. And that's important because the antibodies state estimator has been highly tuned by the amazing people at Antibodies. They've done a really good job with their state estimator, but what I'm trying to say is that there's still a lot more scope for improvement. And this is also sort of a testament that factor graphs are very robust and very efficient, and they can work really, really well. So these are more diagrams showing results on pose and rotation, and more on, this is one more trajectory that I want to show, slightly more complex, but I guess I'm going to skip this for a lot of time. Main thing I want to show is the Atlas walking trajectory. This works, again, really well. We've already seen this in the beginning, so it's just a rehash, but maybe we're more interested in these graphs. You can see on the right-hand side, we're definitely doing better than the baselines that we use. And these are all strong baselines based on estimators that actually deployed on the mini cheetah, for example. So in conclusion, we propose a factor graph-based proprioceptive state estimator, which is robot model agnostic, and modeling the kinematic chain allows for complex joint interactions and model deflections. And you can easily add it to exteroception via extra factors and extra unknown variables. And we presented results in both simulation and hardware. Thank you for attending the presentation. If you have any questions, I'm happy to take.
Thank you very much.